Okay, I think I'll go ahead and get started. Welcome to Seismic Resilient Lifeline Networks. This is part 2 of the EERI Distinguished Speaker Webinar Series. My name is Sam Mengelko, and I am the president of the Southern California chapter of EERI. We're happy to be with you today. Today's agenda looks a little bit like this, and if you can go to the next slide. We're going to talk a little bit about EERI very quickly and about EERI Southern California, and then we will hear a brief recap of Craig Davis's speech or presentation, Operationalizing Lifeline Infrastructure System Resilience to Earthquakes. That was presented last week. It is recorded, so you can see it when that is available. And then we will introduce our panelists and have some panelist presentations. And then we will go into a panel discussion and a Q&A, and then we will wrap up today's program. About EERI, EERI was established in 1948, and the Earthquake Engineering Research Institute is the leading nonprofit membership organization that connects multidisciplinary professionals dedicated to advancing earthquake resilience in the United States and globally. Our members include researchers, practitioners, and students in engineering, geoscience, social science, architecture, planning, emergency management, and community leadership and advocacy. EERI Southern California is happy to announce that we will be having elections coming soon. We have several director positions that will be open to be elected. So we encourage you to participate in that when that begins. And we are also strengthening our university engagement to involve more activities with students and their leadership. And we will be having additional programs and meetings to come. You can always reach us at SoCal@eeri.org if you have any ideas or questions about the chapter. I would like to announce the ASCE Infrastructure Resilience and UCLA Samuel L. School of Engineering ASCE Lifelines Conference for 2021 and 2022. The anniversary of the San Fernando Earthquake Conference, 50 years of lifeline engineering, commemorating the 1971 San Fernando earthquake in the field of lifeline engineering, which really began at that earthquake about 50 years ago. That conference will be held January 31st through February 4th, 2022 at UCLA, and there will be activities throughout the 2021 year. So we're pleased to announce that, and we encourage you to participate. Now I will hand it off to Ann Lemnitzer, our moderator and vice president of the Southern California chapter. And she's going to be moderating today's program. And thank you, Ann. Welcome.
Thank you very much, Sam. I'm going to take over from here, and I will have the pleasure of getting us started on part 1 of this webinar, which is a presentation by Dr. Craig Davis, and it's titled should have practiced that one. Operationalizing Lifetime Infrastructure Systems Resilience to Earthquakes. But for those of you that don't know Dr. Craig Davis as close as I or some of our panel members do, I would like to introduce you to him. Dr. Davis has really a 3-decade-long career at the LA Department of Water and Power and worked there as Departmental Chief Resiliency Officer, Seismic Manager, and Geotechnical Engineering Manager. He also developed the comprehensive Los Angeles Water System Resilience Program, which he will share a little bit with us today about the program and the implementation. He has served on professional committees, including the Building Seismic Safety Council, the National Earthquake Hazards Reduction Program Advisory Committee on Earthquake Hazard Reduction, and ASCE's Infrastructure Resilience Division. Dr. Davis has published more than 150 technical papers and investigated numerous earthquakes. He has a long-standing successful career that has been honored by various societies. For instance, he won the ASCE 2016 Laval Lund Award for practicing lifeline risk reduction, as well as the 2020 Charles Martin Duke Lifeline Earthquake Engineering Award. And what we'll be part of today is the EERI Distinguished Lecture Award. And that award is actually an annual award that's really given to members to recognize and encourage communication of outstanding professional contributions of major importance for earthquake hazard mitigation. And we're happy that Craig is willing to share his lifelong experience with us today, and look forward to learning from him. We will give you the opportunity to ask questions at the very end during our Q&A panel session. And before Craig starts, I would like to remind everyone, please enter your questions in the Q&A section of this Zoom box. You will see that on the very bottom on your screen, not in the chat. And if you have a question for a specific panelist, then just say for Craig or for Dawn or for John, and then add your question, and we'll try to address as many questions as we can. If you would like to comment or have other technical issues during the presentation, or can't hear or need assistance with anything, then please use the chat box for that. And with that, we're ready to listen to Craig's presentation. And I'm going to unshare so we can see Greg in full action.
Hi, my name is Craig Davis, and today I'm going to present the EERI Distinguished Follow-Up Lecture titled Seismic Resilient Lifeline Networks. The 2021 EERI Distinguished Lecture titled Operationalizing Lifeline Infrastructure System Resilience to Earthquakes was given on March 24, 2021. It is available online at the EERI YouTube channel. This lecture for the Southern California chapter provides more detail on operationalizing resilient networks. It's a standalone presentation, but does draw from the main lecture identified above. Today, I'll be presenting to you information on the Lifeline infrastructure systems and networks, resilient network attributes, an example application for the Los Angeles water system seismic resilient pipe network, potential applications to other Lifeline systems, some conclusions, and then finally some references applicable to the presentation. Infrastructure systems are the physical and organizational structures and facilities needed for the operation of a society or enterprise. Lifeline infrastructure systems are a subset of the total set of infrastructure systems, and they include water, wastewater, stormwater, electric power, communication, gas and liquid fuels, transportation, and solid waste systems. These are social technical systems, meaning that Lifeline systems include the physical infrastructure and organizations that manage them. Today, I'm going to make a distinction between a system and the network. The systems are as previously defined in the prior slide, meaning they are social technical systems and have human technical interaction. The networks in this description, in this presentation, will be the physical components making up the Lifeline grid used to deliver the services. The discussion is focused mainly on the technical characteristics, considering how they relate with and support the social and organizational aspects of a resilient system. The social and organizational aspects are critical to a resilient system, but not discussed much in this specific presentation. Let's review some resilient network attributes. A resilient network is designed and constructed to accommodate hazard-related impacts with the ability to continue providing services or limit service outage times tolerable for the community recovery efforts. They accommodate damage and adapt to provide critical services to the community. The attributes include supply links, robust and reliable components linking supplies with critical customers, redundancy and isolation capabilities. They are easily repaired. They provide a rapid service restoration. They account for the entire set of network components and their post-event interactions. They transform to utilize arterial subnetworks. They are able to incorporate advanced and emerging technologies and utilize smart systems. They're designed to meet recovery objectives, meaning that they go beyond the safety objectives. Resilient networks account for the spatial distribution of critical customers within service zones. They recognize that damage may not be prevented in large earthquakes. The concepts are applicable to existing and new systems, but existing systems may require mitigation efforts to meet resilience objectives. This discussion intends to qualify, I emphasize qualify, what makes up a resilient network. The quantification is undertaken using performance-based design concepts, which is beyond the scope of this specific presentation. let's move into some concepts on operationalizing lifeline resilience. So the attributes previously described are applicable to all lifeline systems. I'm going to give an example of a seismic resilient pipe network as applied to the Los Angeles water system. The seismic resilient pipe network is a strategy to improve the existing pipeline network. The Los Angeles Department of Water and Power has previously focused on the other components, for example, reservoirs, pumping stations, and treatment facilities, but has not looked at how they all interlink through the pipeline network to provide services to the customers after a major earthquake. So the definition includes all 7,000 miles of pipelines in the LA water system, not just the seismically robust pipes, and how all the pipelines and other components interact to meet performance objectives. They transform the existing water pipe network into an adaptable seismic resilient pipe network that can restore water services after an earthquake, meeting the performance criteria. This requires the involvement of hazard resilient pipelines and isolation capabilities. I'm about to present to you a video that was prepared by the Los Angeles Department of Water and Power that summarizes and overviews the critical aspects of a seismic resilient pipe network as they are applying it.
At LADWP, we're committed to delivering clean and reliable water to our customers. But what does reliable mean? It doesn't just mean delivering water when it's a nice 72-degree and sunny day. It also means delivering water when conditions aren't ideal, like after an earthquake. In a city as big as Los Angeles, that's no easy task. An earthquake can break some water pipes, therefore interrupting water service. That's why we're working to build a seismic resilient pipe network made up of earthquake-resistant pipes. Unlike our traditional distribution pipes, whose joints could possibly separate as the earth jolts around them, earthquake-resistant ductile iron pipes are fitted using longer joints that allow the pipe to move without separating. And if the earth moves a lot, the pipe will lock into place and then pull on the next pipe and the next pipe, like a giant chain allowing the pipeline to stretch and continue to be in service. In order to make our system seismically resilient, our plan for the future is to use these pipes to create a grid across the city, a seismic backbone. This will not only help provide even more reliable water for firefighting, this network will allow us to run lines to critical emergency services like hospitals, firefighters, and other first responders, so that even if other pipes break within the grid, we'll still be able to get water to the places that need it to serve the community during a natural disaster. These efforts are tied to the city's resiliency plans for lifeline systems and are being designed and executed in the most cost-effective way possible. The whole backbone will not be put in place at once. Rather, we'll map out the grid and install an earthquake-resilient pipe when the original pipe has reached the end of its usable life and needs to be replaced. This will allow us to create a resilient system over decades while still keeping costs down, ensuring that when a big one occurs, we'll have our services available to help those that need help right away, and also that we'll be able to get our city back on its feet and back to normal as soon as possible. To learn more, visit www.ladwp.com.
Okay, so that video provides a good overview and summary of how the Los Angeles Department of Water and Power is developing the seismic resilient pipe network. But I want to give you a little more detail on some critical aspects of how the resilient pipe network is being developed. So first, we need to identify seismic resilient piping systems. Once we have those identified, we can apply them to the transmission and distribution subsystems as identified in this diagram. For the transmission subsystem, and you need to link critical supply lines from the water and treatment sources to each pressure zone. For the distribution subsystem, there needs to be a layout of an arterial subgrid for distribution pipes in each pressure zone. From that arterial subgrid, we need to connect important water system links and the critical A and critical B customers. So critical A customers are defined as those essential for public health and safety. An example is a hospital. Critical B customers are defined as those important for community resilience, for example, a school. The resilient pipeline arterial subgrid dimensions are recommended to be defined by the fire department's capability to relay water through hoses. So, for example, the LA Fire Department can move water a maximum of about 1 mile, which means that we can lay out the grid at a maximum of about a 2 mile by 2 miles. For high-risk areas that need to meet emergency distribution needs in residential areas, we need to limit the grid to approximately maximum of about a 1/2 mile by 1/2 mile. This slide shows the next generation of resilient pipelines that have been developed over the past few years, and new concepts continue to be developed. I don't have time to go over these in great detail. In the video, you heard the LA Department of Water and Power refer to ductile seismic earthquake-resistant ductile iron pipes. In that system, they tend to use ductile iron very commonly in the distribution system and steel in the transmission system. You see both ductile iron and steel here, as well as other types of materials, including the plastic types of pipes, elastomeric pipes, and in situ linings. All of these are actually being used in one form or another in the LADWP system and can be utilized in other water systems to create resilient networks as well. In this slide, I'm showing a map of the city of Los Angeles and the 120 different pressure zones making up the LA water system, along with the transmission lines or the trunk lines that move bulk treated water to different areas in the city. So those are the red lines and the blue lines shown in the map. The red lines are those identified as being most critical to provide water to each pressure zone. We've also taken a look at some example distribution system pressure zones. For example, this one shows the 947-foot pressure zone, and an evaluation using the criteria for seismic resilient pipe network is already defined, identifies that about 63% of the distribution pipe should be replaced with seismic resilient pipe. In the 579 zone, about 40% of the distribution pipe should be seismic resilient pipe. In the 325-foot zone, similar amount, and in the about 47% in the 240-foot pressure zone. So what we find by looking at these, that we have a range of about 40 to 60% of the distribution pipe, or on average maybe 50% across the city of Los Angeles of the distribution pipe should be seismically resilient pipe. These concepts may also apply to other systems, but the issues related to the hazards and what community exists within each pressure zone is important to making a difference in the total number of seismic resilient pipes. But what it does identify is that not all pipes need to be seismically resilient to create a seismic resilient pipe network. Now let's move on to take a look at, to discuss some resilient network applications to other lifelines. This discussion is not intended to be comprehensive. Each network within every system may have different areas of focus for improvement. Not all systems are the same. So for example, electric power, the systems may want to look at designing beyond robust components to provide reliable supply to critical customers. They may want to use microgrids as a local supply source, useful after an earthquake. They may want to use resilient buried conduits, similar to the resilient pipelines I've presented. And they may want to integrate smart grid. Wastewater systems may want to look at proper weighting of robust components versus redundancy, or the lack of redundancy in those systems, the use of hazard resilient pipelines, and links or methods for alternate wastewater treatment and disposal. Natural gas systems may want to look at designing beyond safety using recovery objectives, the integrating of source, refining, transmission, and distribution subsystems, and using robust pipelines to link the transmission to critical customers' connections in their distribution systems. Transportation systems may want to look at integrating of multimodal systems, redundant lines, robust bridges, tunnels, and stations, and design critical ways, meaning things like emergency routes, for all potential earthquake hazards. And communication systems may want to look at integrating multimodal systems, emergency interlinking of provider networks, redundant lines, and larger power storage at critical cell towers. So in conclusion, resilient networks accommodate damage and adapt to provide critical services to the community. They recognize that we may not prevent damage, but can manage a system to provide services to customers when needed. A resilient network supports the social and organizational aspects to improve community resilience. An example was provided on the water system seismic resilient pipe network applied to the city of Los Angeles. And the concepts of a resilient network are applicable to all networks within Lifeline systems, and each may need different areas of focus for improving existing or new systems. And in conclusion, and finally, I want to just leave you with these list of references which are applicable to different parts of what I just presented to you. Thank you for your time.
Thank you so much, Greg, for this first part of your presentation. And let me go ahead and share my screen again with you so that we can move on, because we still have a few different perspectives for you in order from various different Lifeline systems. As a reminder, you can enter your questions for Craig and all the other panelists in the Q&A box. You can start doing so now, and I will address them all together when we discuss with the other members of the panel. I am going to go ahead and I will start introducing one by one, and then we will hear the different perspective with a very brief PowerPoint presentation. Our first panelist is John Shamma. John is the Engineering Planning Section Manager in the Engineering Services Group at the Metropolitan Water District of Southern California. For those that are with me here in Southern California, known as our MWD. Recently, John focuses on Metropolitan Seismic Resilience Program, which evaluates and recommends measures to ensure that water deliveries will be maintained or quickly restored following a significant seismic event in the Southern California region. And with that, John, we are looking forward to hearing your perspective. I'm going to ask you to come on if you haven't yet. There you are. Very well. And let's get going with your slides. And you give me an indicator when you want me to move on.
I will. Thank you. Good afternoon, and really thank you very much for the introduction. I think on the behalf of Metropolitan, I would like to thank EERI for putting on this event and really inviting Metropolitan to participate. It's an honor to be on this panel. Can we go to the first slide, please?
Of course.
Metropolitan has in place an overall strategy that ensures water delivery reliability. The strategy was developed in 2007 in a joint effort by Metropolitan and its member agency. As you can see here on the screen in front of you, the strategy encompasses 5 key components. A water supply reliability component that addresses Metropolitan's ability to supply water to meet member agency demands under all foreseeable hydrological conditions. A system capacity component that addresses Metropolitan's ability to convey, treat, and distribute supplies to meet demands under peak conditions. An infrastructure reliability component that addresses Metropolitan's ability to maintain facilities in a state of readiness to ensure system deliveries. A system flexibility component that addresses Metropolitan's ability to respond to short-term changes in water supply, water demands, and water quality, and the ability to meet member agency water demands during planned and unplanned facility outages. And finally, an emergency response component that addresses Metropolitan's ability to respond quickly to unplanned outages to restore service. We believe by addressing each of the 5 components of reliability, Metropolitan has developed a robust approach to ensuring the overall system reliability for its service area. Included in these components is Metropolitan's commitment to development of projects that are resilient, sustainable, and that can also account for climate change. The second slide here shows our seismic resilience strategy. Southern California, as everybody in this event knows, is crossed by numerous faults capable of generating large earthquakes. This is a fact that Metropolitan has recognized since its inception. And it is the reason why early Metropolitan engineers included within the design of the Colorado River Aqueduct back in the 1930s measures to mitigate potential damage from fault ruptures at those locations where the aqueduct crosses fault zones such as the San Andreas Fault and the San Jacinto Zone. Over the years, as understanding of earthquakes and earthquake forces and earthquake design has improved, Metropolitan has continued to adjust and expand its approach to seismic resilience. Today, Metropolitan employs a comprehensive seismic resilience strategy with the goal of limiting the impact of earthquakes when they occur and maintain water service to our member agencies. Therefore, Metropolitan proactively improved the seismic resilience of its facilities through a multifaceted approach that consists of the 5 components you see on the slide in front of you. Let me go through these components one by one. The first component is a planning component that strives to develop and maintain a diversified water resources portfolio and emergency water storage. For example, Metropolitan maintains in-region emergency storage in the event that the region's imported water supplies, all of which cross the San Andreas Fault, by the way, are damaged and unable to convey water. The second component is the engineering assessment and infrastructure upgrades component. This component is designed to mitigate seismic risk to our infrastructure. For example, it calls for conducting vulnerability assessments to identify potential impacts of seismic events on the system. These assessments often lead to the upgrade of existing infrastructure. Third is the operations and emergency response component. Recognizing that damage may not be prevented in large earthquakes, the operations and emergency response component maintains Metropolitan's effective emergency planning and response capabilities. It, for example, incorporates operational flexibility in our system that allows for temporary shutdowns in our pipeline with minimal impact to member agencies. The component also promotes flexibility amongst the member agencies. We encourage our member agencies to connect or interconnect their systems and develop local resources. Under the emergency response component, Metropolitan maintains in-house repair capabilities through its machining, fabrication, and coating shops. We also keep on hand a very well-trained construction forces that can respond and repair 2 major breaks simultaneously. Metropolitan has also developed an emergency response plan to document the assessment and reporting guidelines following a seismic event, as well as the structural hierarchy of the response teams and their responsibilities. We also conduct annual emergency response exercises to train staff and identify areas of improvement. In the year prior to COVID, we conducted 75 of these exercises with our partner agencies. The fourth component is the interagency partnership component. It is designed to help in establishing a regional-based approach to responding to emergencies. As an example, Metropolitan has engaged with the Department of Water Resources and the Los Angeles Department of Water and Power to form a seismic resilience water supply task force. As the owners and operators of the 3 aqueducts that import water into Southern California, we share one common concern. All our aqueducts cross the San Andreas Fault. And so this These agencies get together to improve their understanding of the seismic risk posed to the system and to coordinate their efforts following a seismic event. Metropolitan is also party to a mutual aid and mutual assistance agreements with the state and local agencies to share resources during emergencies. And finally, a reporting requirement that shares information with member agencies in order to improve knowledge transfer and collaboration. Today, these components are the backbone of Metropolitan's seismic resilience strategy. Metropolitan defines resilience as the ability of the Southern California community to recover from a stressful event. By implementing Metropolitan's reliability and resilience strategies, not only does Metropolitan address the physical conditions of its asset, but it also prepares the organization and its staff to speed up recovery following a distressful event. I think with that, I'm going to turn over the event platform back to Anne.
Thank you so much, John. And we'll be happy to answer questions that we have been receiving for you in the session that's going to follow these little presentations. Now we would like to move on to a perspective from the Southern California Gas Company, and our speaker and panelist today is Mehrshad Ketabdar. Mr. Ketabdar has more than 20 years of experience in structural engineering, design, and construction of infrastructure in many fields, including oil, gas industry, in the gas industry, water and wastewater industry, fossil nuclear power plants, and high-rise industry. He managed small projects as well as big projects, and we're talking about projects up to approximately 2 billion and higher. He is a licensed structural engineer and a civil engineer in the state of California. He is leading the civil and structural team at the Southern California Gas Company and is a member of ASC 7 and 41 seismic committees. Mehrshad, the floor is yours. Thank you for presenting to us today.
Good afternoon. So today I'm going to talk about the seismic design for gas line. Typically in a Southern California Gas Company, we have different departments to manage the seismic aspect. One is a risk assessment team. Basically, they look at the risk and evaluate the risk and prioritize the projects based on the risk. Then we have an emergency group. They take care of when after the fact, things happen, how we can manage all the emergency aspect. And I myself, I'm working for a design group. So I'm going to concentrate on a design aspect of the gas lines, and basically both transmission and distribution gas lines. Next, please. So when we deal with the seismic, the strategy in the big picture from design standpoint is first avoid the problem. Put your gas line somewhere you have less problem. If there is a fault, try to bypass the fault, not crossing the fault. If there is a landsliding area, try not to cross it. Try to bypass it, go to the place you feel is safer. If you cannot, then you design for it. Try to design it and look at all the seismic forces, deformation, all the aspect of the seismic design, and try to design for it. If you cannot, or it's kind of, and then I'm going to go over it a little bit in details, then we try to mitigate it. So basically in Southern California Gas Company, we try to, obviously to be in compliance with the ASCE 7 code or CFR 49-192 or ASME code. Basically, those are the codes we are using either for a structural aspect or for gas pipeline aspect. And the way we do, the first thing we try to do the data gathering. And that means we look at the location of the pipe, how important that pipeline is, how many people we are serving in that area. Are we crossing the residential area? Are we crossing the farming area and no one lives in this area? So we try to prioritize from, in a way, in a building design, we call it importance factor. Here we look at the, pipe 1, category 1, category 2, category 3, and category 4, based on the importance of the line and all these requirements. And then we try to gather the geotechnical and geohazard aspect of the project. What type of soil we have? Are we in a landsliding area? Are we in a crossing the fault? And even when we identify we are crossing the faults, we are looking at how much deformation the pipe can cause. And that's something interesting. And actually, I'm going to go back to what Craig mentioned in his presentation. So when we are crossing something like a San Andreas fault, that fault can cause deformation up to 16 feet. Depends on the risk. Obviously, we're talking about performance-based design. Depends on, are we talking about 100 years earthquake, 1,000 years earthquake, what type of earthquake we're talking about here. But typically the design, if you look at the 2,500 years, return period of earthquake, we're talking about like 16 feet deformation or rupture. That's huge. So those are the challenges we have. What Craig mentioned, and in water industry especially, and also in even oil industry, they have some sort of connection. Basically, when you have a gas line, water line, you have some sort of joint. So it's a flexible joint. The pipe can move a little bit, so they can accommodate the deformation. The creep because of the fault, or even the fault rupture, or even they have landed, whatever, any sort of the deformation, they can accommodate it. In a gas industry, the difference is we cannot have a flexible or joint connection. We cannot. Everything is a solid pipe. So basically, all the deformation, is going to be applied to the pipe, and we have to design the pipe for that. So that's a challenge. Only because we have this in the gas line industry, because it's a high pressure gas line, and the system is under high pressure. So we cannot have a flexible type of joint. So that's the only difference I can see between other industry and gas line. That's a major issue. Next, please. And can I have a next? All right. So going back to that, so typically when we are designing with the underground infrastructure, like a gas line, when we're going to design them, typically we are dealing with a deformation. So anything above ground, when we design it, we design for acceleration. And typically we calculate the force, and then we design it like a building, a houses, everything, above ground. When we design things underground, typically we design them for deformation. Things causes deformation is landsliding, liquefaction or lateral spreading, and fault rupture. So we discussed about the fault rupture. The way we do the fault rupture, basically we gather the data, we gather the old geohazard information, how much deformation we anticipate, and then we model the pipe in a finite element, nonlinear finite element. We apply the deformation, and we try to see what we can do to maybe thicken the pipe, maybe using the flex, more soft material for trench, or geofoam, some sort of, so pipe basically after earthquake can dance, and accommodate the deformation. So we try to come up with all those as a design. If it doesn't work, remember I was talking about there are another ways to do it, mitigate it. We use the shutoff valve. Basically, we try to put the shutoff valve on the other side of the fault or the area of the concern. The earthquake happens, automatically we're gonna shut it off. So the amount of the gas coming to the system, we can shut it off. So to avoid any explosion, anything, in a, catastrophic basically failure. And then on the other side, we are talking about the other type of movement, like a landsliding. If you are in a landsliding area, because earthquake can cause also landsliding, we try to come up with, how much, the depths of the landsliding, and try to put the pipe below the landsliding failure surface if it's possible, or maybe avoid it, or maybe come up with some sort of piling behind the pipe, so to avoid all these landslide issue. The liquefaction, that's another interesting thing. Like basically, when you have a sandy soil and you have underground water is high, earthquake can cause the liquefaction. The interesting thing is, majority of time, liquefaction is not a problem for gas line. Recent earthquake in New Zealand, actually water and oil pipe and wastewater pipe, they failed because of liquefaction in New Zealand. But gas pipeline, they can accommodate those liquefaction very well. So we do not have that much problem with liquefaction unless you have lateral spreading. You guys, if you know the lateral spreading, basically lateral spreading is the combination of landsliding and liquefaction. You are losing your axial capacity, your shear capacity, everything almost. So typically happens, in a river ravine area. So for those, if we identify the areas in a lateral spreading area, we try to put the pipe on a pile, deep pile below the ladder spreading area, and design it for that aspect. So my presentation is basically was about how we design gas lines, a little bit maybe offset of the other people, but I thought maybe it's interesting to just discuss some technical aspect of the what we do in Southern California Gas Company. Thank you.
Definitely, that was great. Thank you so much, Mehrshad. It's good to hear it from the design perspective as well. We're going to move on. Our next panelist is Don Cutler. Don Cutler is the engineering supervisor with the Orange County Sanitation District in Southern California. In his role, he oversees civil and mechanical design for the Orange County Sanitation District Capital Improvement Program as it relates to their wastewater treatment facilities. Prior to joining the OC Sanitation District, Don served as a senior project manager with over 24 years of consulting experience and specialized in wastewater and water reuse design projects. Don is a registered professional engineer in California and in Texas. He got his bachelor's from Cal Poly Pomona, both here around the corner, and the MS from Loyola Marymount University. Don, the floor is yours.
Thank you, Anne, for that great introduction. And it is a pleasure for me to be here with these other agencies representing OC San. First off, I wanted to say welcome from Southern California for those that might be out of state. And next slide. Wanted to start off with giving a little bit of background on the Orange County Sanitation District. We are located in Southern California, about 30 miles southeast of the city of Los Angeles. Our service area extends over 480 square miles, serving approximately 2.6 million people. We have almost 390 miles of trunk sewer that receives wastewater flow from member cities within our service area. OC San also operates 2 wastewater treatment facilities. First is Plant 1, located in the city of Fountain Valley. Plant 1 receives approximately 120 million gallons per day of wastewater, which is treated and sent next door to the Orange County Water District, where it goes through advanced treatment for indirect potable reuse. Plant 2 is located a little further south in the city of Huntington Beach. Plant 2 receives approximately 65 million gallons per day of wastewater, and both plants are actually located adjacent to the Santa Ana River, which creates a unique risk to our facilities during a seismic event. Plant 2 is also bordered to the south by the Talbert Marsh. Next slide, please. So OC San provides a critical service for protecting environmental health in Southern California. Therefore, it's our culture to develop a robust asset management system that regularly assesses the reliance of our facilities. And we've implemented a strong capital improvement program to ensure that we can provide continuous operations of our collection systems, pump stations, and wastewater treatment plants. To support seismic resilience, General Manager initiated a planning study in 2017 that would evaluate both of our treatment facilities. The primary objective of this study was to identify vulnerabilities within the structures of these 2 plants relative to seismic hazards. But in order to develop a plan to mitigate these vulnerabilities, it was also necessary that we identify mitigative measures and their associated implementation costs, as well as coming up with a system to prioritize how those facilities would be addressed. And one of the more significant findings is both plants are located on alluvial sandy soils with high groundwater conditions. This is an ideal situation for liquefiable soils to occur. In fact, liquefaction-induced sediment was found in a range between 2 and 10 inches at both of our treatment plants. Next slide, please. Now, because of this proximity to the Santa Ana River and the fact that we have liquefiable soils at both plants, it was determined that we also have a seismic risk of lateral spread at those facilities. Plant 2 also is challenged with being adjacent to a major fault system, the Newport-Inglewood Fault. And this prompted a new study that is currently being conducted to identify potential fault hazards, as well as the impact from those faults. And that figure to the right shows all of the faults going through our plant. That's a wonderful sight, isn't it? Next slide, please. And as a result of all this work that we've been doing, these seismic studies, as well as other studies that we've been looking at for other risk impacts, we've been able to develop a plan to integrate seismic resilience into our capital program. Several of the process facilities that were identified with risks are already scheduled to be improved as part of our planned capital improvement program. So the seismic rehabilitation will be integrated into those projects. However, as a result of the work that we did identify 3 structures that need to be replaced in their entirety. That's because the mitigation costs exceed the value of those structures themselves. We also came up with a plan to launch 5 unique projects that will be executed over the next 10 years that are specific to seismic rehabilitation of our facilities. And as we continue to develop our seismic program within our structures, we will integrate these improvements with other non-seismic risks like flooding and sea level rise that result from climate change. Our ultimate goal here is to develop a robust infrastructure that allows OC-SAN to continue to provide reliable wastewater treatment and service our neighboring communities. Thank you so much, Anne.
Thank you so much, Don. We're going to move on to our panelists from the Southern California Edison, talking about electricity networks. I'd like to welcome Jennifer Pearce to the panel. Jennifer is currently a principal manager in SCE's, what we call Southern California Edison's Business Resilience Department, and she's responsible for the company's business continuity, assessment, mitigation, and resiliency planning programs. Her background is primarily in understanding communities' exposure to the various hazards and threats, and she has extensive experience in catastrophic disaster response planning at both the national and local levels, and with also the private sector. Prior to joining SCE, she actually spent a number of years in Washington, D.C. at FEMA, we all know, leading the national efforts planning for disaster resilience. And she was also part of the core national team working on the implementation of the President's National Preparedness Goal. So in addition to preparing the organization to deal with disasters, she has worked herself on a number of disasters and reconnaissance efforts, from responding to the 2010 earthquake in Haiti, the Hurricane Sandy in 2012, as well as now more recent events closer to home that include the wildfires, but also COVID-19 response efforts and many more, while executing her duties at SCE. Jennifer, welcome to the panel.
Thank you, Anne. I appreciate
There you
it.
are. Perfect.
Yeah, and thank you for inviting SCE and myself to join the panel. It's been great to hear from my counterparts here already. So just a little bit of background. So Anne talked a little bit about my personal background, and I made the leap from working at FEMA on these national efforts to go in the private sector, because one of the things that I learned is getting lifelines back up and operating is the most effective way that we can help communities. It enables people to help themselves more quickly. And so 7 years ago, when I joined Southern California Edison, I joined their business resiliency department. And the company had made a commitment to really start investing in how we identify our hazards and threats and assess the impacts that the company and its communities it might serve against those hazards and threats, and then come up with programs and investment strategies for reducing those threats and preparing to respond and recover from them. So if you can go to the next slide, please, Anne. We have adopted at SCE a lot of the national standards that stem from FEMA and other organizations. And most of our founding principles stem from Presidential Policy Directive 8, which is the national preparedness goal for the country. And the key tenets in there are really around 5 different areas. How do you protect and prevent typically human-caused events such as cyber attacks, physical attacks from occurring? How do you mitigate the impacts of different events and reduce that impact so you don't have to respond as much or recover as much before an event? And then how do you prepare to respond and recover? So this guiding framework is how the company has approached business resiliency as a whole. And obviously living in Southern California, we're one of the largest electric utilities in California. We cover almost half the state, about 15 million people, 50,000 square miles, which to give you a sense is relatively the size of the country of Greece. So a fairly large service territory with a lot of different unique characteristics within that service territory. So we have communities that are in the desert, that are in the mountains, that are in the inland areas, the coast, urban, rural. And with that comes all sorts of different types of unique characteristics that we need to manage through in hazards and threats. So we look across the board at all sorts of different hazards and threats that we could face, but seismic is obviously one that we've been living with for a long time and is something we pay very close attention to. So if you can go to the next slide for me, please. We have always looked at seismic risk in the company. We're about 130 years old. Our infrastructure has been around for a long time, but about 6 or so years ago, the company decided to centralize its program under business resiliency so that we could standardize how we approach our assessments and mitigations across our different business lines. So as an electric company, you would assume we've got electric infrastructure, but we also happen to be a huge building owner. We own upwards of between 300 and 1,000 different buildings, depending on how you classify them. We also have generation assets, hydro assets, peakers, powerhouses, and lots of communication systems. So in this day and age, we all are becoming more and more reliant on technology to run our systems, moving more away from manual processes as our primary mechanism and relying on these systems and technologies. So data centers and the resiliency of those and the networks that connect that communication systems to things like grid control and other are also very important for us to look at. So we look across these 4 major disciplines. That's how we organize the work. And we work within each of the technical areas within each of these. So we're not necessarily the experts from an engineering perspective, but we provide coordination and consistency and standardization for how it's done across the company. And with such a large critical infrastructure portfolio, it's really important for us to be able to understand what's most critical, what's the status of that, and how do we do these macro level assessments to really understand where we need to start drilling in and spending more time and money on further understanding what the impacts could be and coming up with different retrofit or mitigation options to make investments around. Our priority is always life safety. So it's the safety of our workers and the communities that we serve, but also quickly followed by service reliability. You know, after a major event, folks are going to want the power back on. We know we're a critical lifeline. And so really looking at what are our standards for life safety and for service reliability and making sure we're making those prudent investments in both those areas. So that's it at a high level. I know we're going to have Q&A, so I'll leave most of left of the time for that. But I appreciate you having us here and look forward to the questions.
I'd like to thank you for participating. So with that, I'm actually going to lead over and I am going to unshare my screen. So we invite all our panelists back in live, and I will start pulling out some of the questions. And if you still want to type in your questions, feel free to do so. We'll be continuously receiving questions. They are, don't worry, they will only be seen by myself, so you can ask away whatever you want. I will have the challenge to filter through them. And I would also like to invite Craig back on live. So he is not just our virtual presenter, he does exist in reality. And here we go. So everyone should see all of our panelists again. Jennifer, if you could come back on as well, that would be great. And I am going to start asking for a few questions. Craig, I'm going to start with a few questions for you that have come in. since your talk was the first one. And here is the first question. For zone 947, you say that 63% need to be seismic pipe. Briefly, can you please briefly describe the criteria used to get 63%? For example, is it all pipes that fail in earthquakes, or is it some fraction, like 10% can fail or still function? Also, under what level of earthquake? Is it 2,500 euro or 500 euro return period, etc.?
Okay, thank you. That's a great question, and I'm happy to clarify. And I'll start with the last part first. I mentioned in the lecture that I was not addressing the quantification, which is under performance-based design, but that's a quantification type of question. Without getting into the detail, essentially for the critical A customers, we're targeting a design level of 2475 or greater, which I won't get into. And for critical B customers, which are needed for resilience of a community, a minimum of 1,000-year hazard return period. But then how do we figure out the lengths of pipe, or the percentage of pipe? So it really was just a total percentage of pipe, right? The final calculation is the total percentage of pipe that we need to be robust to meet those minimum design requirements to the total number, right? So it's just a ratio of two numbers. But what your main question is, how do I get that numerator? Right, the denominator is easy. You just use GIS and surround it and have the technicians give you that number. It's the upper part. So I described it in an overview, but not in detail. So the criteria was listed in the lecture, but only at a very high level, not enough for you to actually know how to answer this question. So let me go through this real quick. The idea is to create a reliable set of pipes. It doesn't start with the idea of which ones are going to break. It starts with the idea of having a reliability of pipes that can get water from a source to the customers when they need them. And in this concept, not all customers are equal after a major event. You have to prioritize them. You can't restore all customers at once. You can't ensure that there is no damage. So the idea is to just create a reliability. So if you're using resilient pipes, some of these pipes in the water system, and I will agree with the distinction that Mehrshad made, but in the water system, some of these pipes have never failed after being moved 15 to 20 feet. They have not failed. They didn't even leak. They just keep working. So highly reliable. And that's after 40 years of work of them being in place. So they're highly reliable. Doesn't mean they won't in some future earthquake, but you can have a high reliability that it's very likely that they can work. So if you're using these types of pipes, then you have this reliability. So you want to start with a grid for which you can, I just started in that calculation of what is the maximum spacing of a grid, and then how do you begin to lay out that grid? So we use the LA Fire Department. So there's a reference to what that is. LA Fire Department can move water a maximum of 1 mile. So we took a concept of, all right, under extreme conditions, they can move it at maximum of 1 mile. So if we put a grid at maximum of 2 miles by 2 miles, theoretically, we can get water to any point from these reliable pipes to any point into the city, right? So then we laid out a grid that made sense based on the existing network. So mostly it was the big arterial streets. That's where the bigger, the 12, 18-inch pipelines are for distribution in a LA water system, but some of them are actually 6 and 8-inch pipes, and that can be used to move firefighting water supplies. Then we identified where are the critical A and critical B customers. So there's a greater definition. I just gave you some examples. Where are they in this? And then we took water from that grid layout, or we took the same reliable pipes, from that grid layout that I just explained, to these customers where they're at. So these are the hospitals. These are not the bowling alleys. These are the hospitals. These are the emergency evacuation centers and so on. Things that actually don't move within 30 to 50 years. They're there. When they're there, they're there.
right? You don't see hospitals moving very much. So it's very reliable that you know where your network will be. Then you also take the grid and you connect it to every source of supply that you can. So that you have a reliable way of getting water into this network and a reliable way of getting that water in the network to the customers that they need. So in this concept, I haven't identified how I prevent all pipes from being damaged. I'm not even looking at how many repairs there are. I'm looking at how we get water to the customers when they need it, right? So there's other components that I'm not getting into here that you have to have response and recovery and isolation and a whole bunch of other items that I had listed in there that have to be linked. But that's the basic idea of counting up the pipes. So now that you have this layout that I just explained, you just take that final ratio. You count up those that you need to have reliable, divide it by the total number, and that's how that percentage came out for each of those example pressure zones.
Thanks, Craig. There was another question that was right along those lines with how did you establish the percentage of pipes? And then you just addressed that in how you got to these numbers. But one more quick question to follow up that just because it plays right into this question is the video stated that for cost effectiveness, seismic resistance pipes will be installed when old pipes need to be replaced. Did it mean replaced after they have been damaged by an earthquake? I guess you partly answered that already, or for other service conditions. If the latter, how many years is it estimated that it will take for the seismic resistant pipes to be installed, before an earthquake happens, or probably on a larger scale? I imagine this question is addressing. That's a hard guess.
Yeah. So that was in the DWP video, I believe, where that was stated. And the idea comes from, in fact, I would, let me give a little background to this. That whole concept related making resilient asset improvements related to the asset management and the pipe replacement program. Because as an organization, the DWP, and I'm sure all of the others, Southern Cal Gas, MWD, Orange County Sanitation, Edison, you can go up north, PG&E, south to San Diego Gas. All of these organizations as having to manage these huge number of assets, they have a serious issue trying to figure out how to prioritize and spend the money. There are pressures on a daily basis to spend more money than they have. And yet we are a group, and there's a huge number of advocates saying, but you have to do this to make these improvements for resiliency. And yet they're worried about just making sure they have reliable services on a daily basis. This is something that most people don't actually recognize. So I spent a career trying to convince the LA Department of Water and Power that you should be doing all of this. I probably went 100 different paths, probably more than that. All failed but one. That one is related to this question, where I realized, look, they're being progressive and they're looking at what types of assets should be replaced as they're aging and needing to be replaced now, so that they work better for the future. Not necessarily, they were trying to be progressive. Let's not replace them with what we've been doing in the past. We will do that only if that's the most appropriate asset for the future. If it's not, like seismic pipe, right? So when we built it, there wasn't seismic pipe didn't exist. Now it exists. It's a fairly recent concept in the United States. So what do we do? So the idea is to not force the agency to spend all of their money in 10 years. You cannot replace 7,000 miles of pipe in a 10-year capital improvement program. It takes actually 120 years. So that's part of the answer to your question. So identify, like I showed in those maps, which pipes need to be seismically resilient, have a comprehensive program to create a resilient system. And look at the resilient networks, which I defined in this, it's not always defined this way, but I defined in that lecture as just a hardened infrastructure. But as everybody else described, it's both the assets, the infrastructure, and the people, is how they all work together, is how you create resiliency. But identify which ones you need. And as they are, use that as a category in your asset management program. So it actually bumps it up as a higher priority, at least ever so slightly, when you're accounting for the seismic hazards, and account for other hazards as well, by the way, not just seismic. and then identify when they need to be replaced. So if one needs to be replaced today because it's leaking a pipe, well, if it's one of these that I just explained, it needs to be part of the seismic resilient pipe network, arterial subnetwork, then you put it in with seismic pipe. If not, maybe it's okay to repair later, but you need to isolate it. So that's the idea that supports that statement that was in the video.
Yeah, very well. John, do you want to comment from an MWD perspective? This kind of goes in the whole line with how do the agencies, envision, like Craig mentioned, emergent technologies to improve the network resilience and create a more resilient and sustainable network. Any comments from your end or from MWD's perspective?
Sure, absolutely. I think I would say that Metropolitan is very keen on innovation. The engineering group maintains an innovation plan, and the plan strives to identify and develop new technologies for use by Metropolitan. We participate in things like all utilities and Water Smart, among other innovation groups, and we regularly exchange ideas with other utilities, locally, nationally, and internationally. And to follow on what Greg was saying, for example, recently we made a lot of progress on earthquake-resistant pipeline, and we have worked with manufacturers like Kubota and I hope I'm saying their name correctly, JFE, in testing their pipelines for use in our system. We've identified now projects where earthquake-resistant pipeline will do the trick for us, and I can tell you that we've already received the first delivery of earthquake-resistant pipeline for a segment of the Colorado River Aqueduct. The challenge we have with earthquake-resistant pipeline, that it works very well on a smaller scale, but when you come to Metropolitan and the average size of our pipeline is 12 feet in diameter, it is tough, to make an earthquake-resistant pipeline work. But we're making it work in this particular project. We're double-barreling the projects to take advantage of this pipe. We also seek opportunities to participate with other agencies, organizations, and academia in testing new products. And we maintain our own testing facilities. And we're now considering construction of additional testing facilities to help us test new technologies to use in the water business.
Yeah, great. Thanks, John. The emergent technologies are a hot topic, and we have another question aligned for that as for Mehrshad. Since you briefly touched on, the design of the pipelines being so different, I'm going to read the question for you. You noted that flexible joints or couplings are not recommended for natural gas systems. Fully welded fused systems are desirable, as older or legacy systems included joints that remain a challenge today. Are you aware of situations, for instance, fault crossings, where a flexible component might be considered to accommodate large movements for a gas network? Are there innovative or proposed solutions that might be considered looking forwards for specific locations, like a bridge crossing or other similar?
Good question. The flexible connection, they are not considered for a good reason, because they are not good for the pressurized gas. So because the line is under pressure and you're gonna have hoop stress because of that, so the flexible connection, they're not developed well for that aspect, at least. But there are technologies, as mentioned in the question, for basically one of them is bridge crossing. Obviously, we can take the pipe out, up, and then put it on a pile and just design it for that as a above ground structure. That's and cross the area. Obviously, there is one very good example, and actually it did work after earthquake in Alaska. They brought the pipe up and they put it like some sort of, so the pipe can kind of can dance and move after earthquake. And in a fault area, and actually fault ruptured and pipe basically survived. So that actually happened in the past in Alaska. So there are things like that in the real life. Most of the time we use geofoam because the thing really causes damages to the pipe is pipe, because of the deformation of the soil and the fault, they want to move, but the pipe is restrained by trench area with the soil around it. So it's restrained, it wants to move, but there is a restraint, so it causes the kind of failure for the pipe. So if you make the area flexible and let the pipe kind of, always use the word dance, or kind of like easily can move, then you can accommodate it. And the geofoam material is their perfect material for that, because let the pipe kind of move. And then the depth of the trench material, how deep it's going to be, because when you change it, the restraint of the pipe is going to be different. It's all about the restraining, how we restrain the pipe. So if we fix all those, we can accommodate it. But in real life, the only cases I know the fault crossing really worked, it was in the case of Alaska gas line.
Mm. Thank you. To follow up on that, here's another little detailed question. My understanding is that the majority of seismic gas leaks are at the customer meter sets. Yet the installation uses standard drawings having little to no engineering. I think improving meter installation might be a cost-effective action. Do you agree with that?
So there are two different things here. Southern California Gas Company, we deliver the gas to the customer. So technically, anything happening in the customer's facility is their property. It's not our business. We are not even legally allowed to tell them what to do. So we just transfer gas to them and they take it from there. From that side, not as a gas company employee, I'm telling you some facts of that, because it basically is it's the customer's business from that point. But the shut-off valve also works, because then if something happened in your gas line system at your home, then you can shut it off. Also, one of the things is we need to discuss it here is post-earthquake fire. A lot of time, historically, especially in San Francisco earthquake, what happened is the earthquake itself, the damage was less than the fire after the earthquake. And majority of time, what causes the earthquake is an electrical system fails somehow, or something related to the gas, not really the gas line. Like if you have a heater at home and the heater, basically flip-flop, just turn over, and then then it can cause the fire, or a stove at home. Those type of things you have can causes the fire after earthquake, and then that could be even out of the hand more than earthquake itself. So a lot of time, things like bracing your heater at home or putting shut-off valve to just avoid the fire after earthquake can make a big difference as a like a housing department or something, if they help that out. In a commercial way, in the state of California, is kind of there is a regulation actually. They put those shut-off valve, and then in a hospital we put all the heaters should be bolted down, make sure they're not falling, or all these things. So if we follow ASC 7, all those requirements to make sure everything is really well connected or positively braced, is the word ASC 7 uses, then we should be fine. But this is not really gas company business.
Okay, thank you for clarifying that. I think that was helpful. Jennifer, I want to ask you another question that came up in the question and answer box. It's more a strategic planning type of question. The question is, if you could please contrast your program from Southern California Edison to that of PG&E that serves the northern part of California. They seem to have more challenges.
Yeah, I don't want to speak on behalf of PG&E and what their programs are like, but I'll say, we as the three major IOUs and electric IOUs in the state, PG&E, SDG&E, and Southern Cal Edison are routinely in touch and benchmarking and trying to learn from one another and improve, but we're also very different. So PG&E has gas, Southern California Edison does not have gas. So we'll organize a little bit different. At Edison here, we've made a very deliberate effort early on to adopt the principles established at FEMA and the National the management system and all of that. And PG&E also is in that direction as well. So we're I think very similar but different at the same time. So unless there's a specific question or area that they're interested in learning about, I think it's hard for me to comment on their programs.
That's totally understandable, but you provided us with the perfect lead in to a few of the next questions that kind of address that, that there is a much larger community. And several of the questions that came in, how can Lifeline communities establish a common, perhaps minimum seismic performance target level? And what are the challenges of accomplishing it? And we had similar questions like, how does your agency or network look at the hazards? Like, do you look at it as a single event, as a combined event, and then combined event just related to your agency and to your network, or the whole topic of interconnectedness? Is it possible to establish a minimum seismic performance? And how could that potentially look like working towards one? Or are we, should our primary focus be right now to really look at the singular hazard events of each, with respect for each agency, before starting to go completely global?
I think I'll start, and then I would love to hear from someone else in the panel as well. But this is a challenge not just in the seismic space, but any natural hazard space, defining what the goalpost is. In California, we're seeing this with wildfires. There needs to be almost a external entity of sorts establishing and working with the different organizations to figure out what that common goal is, so we can all work towards it together. I think we've got a lot of standards out there, especially in the seismic area, through IEEE and ASCE and all of those that we lean to heavily. Seismic's a little bit more defined than some of the other spaces. I think that what we're always struggling with is keeping ahead of the science and technology. It takes a while for standards to change and things to evolve, and making changes to assets and infrastructure is a long-term process. And so you're continually having to evaluate and see if you're up to those standards over time. So that's my take on it. I do think it's a hard question to answer, and something that we probably need to think about as a community.
Yeah, if it's a hard question to answer, we'll shove it over to Dawn.
There you go.
How about that?
I wish I had a better answer than that. One of the things that we've struggled with as a district is to keep up on the ever-changing seismic codes and how that influences the design within our structures. One of the things that we've tried to look at recently is just the risk category. Wastewater by code is identified as a risk category 3. However, we realize that our facilities are essential for the protection of the environmental health, and perhaps that really isn't appropriate for our facilities. And we're looking at ways to enhance the design of our facilities. We do have the seismic risks. We've also done studies to look at other risks like sea level rise, and our Plan 2 not only has those faults going through it, but it's also very close to the ocean as well as the Talbot Marsh, and so we're subject to sea level rise, and we've developed long-term plans to mitigate that by putting in seawalls that will serve two purposes. They'll serve protection against sea level rise and that risk, but also be designed to mitigate lateral spread by basically encapsulating the site and preventing that lateral movement to the Santa Ana River and the marsh. So, but it's not an easy solution, and there's a lot of money involved. And I think Craig rightfully pointed out, you have to appropriately allocate your funding for these assets and plan for them over a reasonable time so that you accomplish your end goals of seismic resilience, but at the same time, you're not implementing these $100 million capital programs just for one purpose. You know, we've got to deal with the seismic, but we also have to deal with aging infrastructure. Some of our facilities are 56 years old, and these other risks. And so it's a challenge and something that we are very serious about and are dedicating a lot of resources internally to resolve it.
Yeah. Let me see here. We are almost approaching the end of our webinar, but we have received so many questions here. Thank you, everyone, for that. Let me ask you a question maybe every panelist can comment on very briefly, even though we do live in Southern California, and this is a heavily seismically prone area. What do you consider as the most significant potential natural hazard impact to your respective Lifeline network? And don't only think maybe local. We all know what has happened in terms of disasters globally. I myself have just returned from the georeconnaissance of the Western European floods, and I, saw damage that, exceeded by far what I had seen in recent earthquake reconnaissance efforts. But specifically for your network, what do you consider the most significant natural hazard impact, and or is it a combination thereof? Like we have seen here. Jennifer, you want to go first?
Yeah, sure. I mean, obviously earthquakes is something we've known about for a while, but not just looking at our service territory. I've been in emergency management for 15 years, and you can just see the onset of these more extreme weather patterns occurring. Whether it's wildfires or more intense rain events and hurricanes. And something that the company is looking very closely at is climate change, and not only how do we reduce carbon emissions to mitigate climate change, but how do we adapt to it and deal with not just the long-term chronic concerns that climate change might face to us, our communities, the systems that we manage, but also how do we deal with the short-term consequences, because we're no longer just planning for climate change, we're in it, right? Climate change is here. We're seeing the onset of these more extreme events. So it's not that things are just going to get wetter and we're going to have more storms. They might be less frequent, but they might be more intense. And so we're having to really look at how we design and plan for the future, with the idea that we might be facing these kind of risks in emergent hazards more frequently and potentially more intensely. And so I think that that's just a new, I hate to use the term normal, but it's a space that we're all embarking on, I think collectively, not just in California, but across the country, across the world, and trying to figure out what that's going to look like and how we design for that future.
Anyone else would like to comment on this one?
For Metropolitan, today is the toughest thing is dealing with droughts and the ability to move water to get it where it's needed. And we're spending a lot of money and energy in dealing with those type of issues. This is also part of a resiliency issue. We look at seismic resilience, but we also look at the drought and climate change and being resilient to the conditions we see today, with the two major watersheds being dry, both the Northern California watershed and the Colorado River watershed, and having the ability to manage the supplies to meet Southern California demands. I think we've done very well in the past. It's good to sit here for once in my career and notice that Northern California is looking at these challenges for the first time more drastically than we are. And we're sitting here in Southern California for all the planning we've done and for all the sacrifice that people in this community have done. I think we're doing rather well.
Craig, I believe, go ahead.
Yeah, so if there's time, I'd like to also spend a few seconds at the end addressing the recovery. So the recovery question, but the earthquake can seriously damage water systems. So just focusing on water there. But I, as the resilience officer for the LA Department of Water and Power, I actually convinced myself that the wildfire, the EERI issue around LA and a whole bunch of other cities, especially on the West Coast, is probably the bigger issue. And then you can expand to all of the climate change hazards, like John talked about drought. And there's issues with fire departments not actually having the ability to fight urban fires at the wildland interface, because it's designed to fight houses one at a time, maybe two at a time, right? So the pressure and the volumes aren't necessarily there. And I was attempting to address that question in the water industry as a whole before I retired, but that's a difficult one to address. I'll leave it at that.
Just have out of retirement, Craig.
Yeah. So if I might, since we're almost out of time, I do want to point out the question. I wanted to point something out to the audience on the issue of common recovery times, right? So service recovery is really important. Congress has actually asked this to be addressed in the earthquake realm under the concept of functional recovery for both buildings and lifelines, and have all lifelines consistent amongst themselves and consistent with buildings. But when you think about it, it is not limited to earthquake hazards. It affects all hazards, as Ginny, I think, politely mentioned earlier. And so there is a need for that. There is a project, a set of projects undertaking that I'm involved with both FEMA and with NIST. We are working out a framework to see how to figure out how to make these consistent. They're not all going to be the same. If you look at New Orleans right now, power is needed before water, right? To get water, you have to have power. So, you know, they're not all the same, but they have to be consistent. So consistent is the key term. And we are venturing into exploring the concept of water in this framework first, as an example, because of the work that I did at DWP is helping to lead the way. And then we will be moving on to all of these. So as the panelists, be prepared that I might be reaching out to you. And as the audience, be prepared that if we're successful, and I would claim that we will be, you will be seeing how we should be moving this forward together for the community to ensure resilient communities, because without consistent lifeline services, you can't have resilient communities. And we will be moving this forward, and it will be how we will all work together for the next decades, many decades.
So no one really gets to retire here on this panel, just to clarify, okay? Because Greg is planning on staying around for at least 5 more decades, as he just indicated, okay? Just make sure everyone is on the same yeah, everyone's on the same page here. Mehrshad or Don, do you have any final comments? Otherwise, I'm going to ask to Sam to wrap up, but please, your 30-second final statement.
Just really quick. This is my first EERI seminar to present at, and I got to say it's very interesting to be with these other panel members. And what I'm understanding is that for each of these different lifelines, they may not have common solutions. We may have all unique problems and unique solutions, even though the threats are the same, the risks are the same, our solutions may be altogether different. So it's really interesting to have this exposure and hear what other people are doing.
Yeah.
Thank you.
That's what I meant earlier. For every system, you know, rapid service restoration means something else that can be accomplished at a different scale, time, and yes, it will remain a challenge. But as Greg just indicated, just wait for a few more decades and we'll all morph it into a solution. Mehrshad?
Well, I just want to emphasize what Craig said. I agree with him. The biggest challenge right now for utility companies in Southern California area is wildfire. It's a big challenge, lots of money and operation and maintenance. It just causes a lot of time and work and money for us, you know, just to address that. So wildfire is a very big issue for us. It makes sense to look at it, different aspects of it. It becomes bigger and bigger. Compared to 10 years ago, I started in gas company. It's just bigger problem now. It's just naturally is happening. It's just bigger and bigger problem for the gas company. I'm sure for majority of the utility companies.
Yeah, thank you very much. With that, I'm inviting our chapter president back on to join us. Sam, there you are.
Hello. Do you want to share your screen, Anne?
Yes, I can.
I think that was great. I just want to thank all the panelists and moderator, of course, who were able to join us, Craig Davis, John Shamma, Mehrshad Ketabdar, Don Cutler, and Jenny Pearce. Thank you so much for joining us today. I think it was a great discussion and very enlightening. Perhaps we need a wildfire engineering research institute.
For sure.
So thanks everyone for joining us. Looking forward to 2 additional webinars on the Lifeline topic in October and November of this year, put on by EERI. And that's it. Thank you for joining us. Everyone have a great day. Thank you.